In this video, I'm going to determine an orthonormal basis for the subspace of R3 spanned by the set of vectors 1, 0, 1, 1, 2, 0, and 0, 2, 2. To find that orthonormal basis, I'm going to use the function orth. The function computes an orthonormal basis for the range of a matrix. So what I will do is I'll enter these vectors as columns of a matrix which I will call A. What we should note is that the input matrix should have linearly independent columns. So in this case, these vectors here are linearly independent, and we are saying those will be the columns of the matrix that I'll be entering. So in this case, that function will work effectively in this case. So what I'll do is I'll go on to my live editor here and then click on code. So for the code, I'm now entering a matrix, which I'm calling A, and that matrix is these vectors is its columns. So it will be the matrix, then open square brackets. So that matrix there would have elements 1, 1, 0. Then go to the next row, 0, 2, 2. Go to the next row, then we have a 1, 1, 0, 2. So that's our matrix there. I can just run to check if I have entered correctly. So we are saying that the matrix A is these vectors as its columns. So the first column there is the 1, 0, 1. Then the second column is the 1, 2, 0. The third column is 0, 2, 2. So I've entered those vectors there as the columns of a matrix A. So I will now go on and find the orthonormal basis there. So I'll call that G is equals to, call the function orth. Open parenthesis, we are saying the orthonormal basis for the matrix A there. Then I can go on and run here. And it is giving us the orthonormal basis here. So what you are having here is the columns of this matrix G forms the orthonormal basis there for the three vectors. What you are seeing there is the result is coming out there as a decimal. But if we want to change that, I can enter this matrix as a symbolic matrix. So I say SYM, change this to a symbolic matrix. Then we have the auth there, then I can run. So what you now have there is the G there is these values now. And what you are saying is the columns of this G, they form the orthonormal basis there that we are looking for. So I can go on and now extract those columns there. So for the first one, I'll call it my U1. So it will be U1 is equals to, and I'm extracting from the matrix G, I'm extracting the first column there. So it will be colon, then comma 1. And I can just go on and run here. And it gives us the U1 is square root of 2 divided by 2, 0, square root of 2 divided by 2. So that's the U1 there. I can do for the U2 is equals to, then G. We are now extracting the second column. So colon, then comma 2. And then for the third column, it will be the U3. And it will be equals to G, because we are extracting the G. We are extracting column number 3. So comma 3. And I can go on and run here. We are having our U2 as elements root 2 over 6, 2 root 2 over 3, minus root 2 over 6. And our U3 is equals to minus 2 over 3, 1 over 3, 2 over 3. So we have these U1, U2, and U3. They form the orthonormal basis. What we are saying there is the U1, U2, and U3, they each have a norm of 1, and they are pairwise orthogonal. We can just try to verify that. If we take the norm of, say, U1, the norm of U1, I can go on and run. and it gives us the norm there is 1. So all these vectors u1, u2, and u3, they have a norm of 1, and they are pairwise orthogonal. That is to say, if we take any two pairs of the vectors and we take their dot product, then it will give us a 0. So I can just try to check for the dot product there of u1 and u2. So it's u1 comma u2. So I can then go on and run there, and it's giving us there the dot product there is a 0. It's saying that u1 and u2, they are orthogonal. So what we have found there, the u1, u2, and u3, that's the orthonormal basis, a set of vectors that each have a norm of 1, and they are pairwise orthogonal.